Welcome back to Introduction to Dynamics. In the last video, we talked about equations and concepts that we will be applying in this video when we do an example problem relating to kinematics of a rigid body. So let's get into it. Last time we talked about these equations just to refresh your memory. Alright, so the problem says if the angular velocity of AB equals 2 radians per second and the angular velocity of BC equals 4 radians per second, what is the velocity of point C where the excavator's bucket is attached? Let's take a look at this image. So this looks kind of complicated, but really it's not that complicated. It's just two rigid bodies attached at a common point. So we've got this rigid body right here, and we've got this rigid body right here, and they both have B in common. So the point B will be key in solving this problem. So if we just go back a second, we can't relate point C to point A directly because they're not on the same rigid body. The equations that we found relate 2 points on the same rigid body. So we can only relate point C to point B. And then from there, we don't know anything about the velocity of point B or anything else about point B besides where it is specifically in a corner frame. So we can relate point B to point A because point B and A are on the same rigid body. And then by using that, we can find the velocity of C because we know that A is stationary. So that gives us a value that we need in order to solve these problems. So let's use this equation right here because we care about the velocity of a point relative to another point. So we need to rewrite this equation. We can't just use it in its original form because this equation is relating point A to point B, but we care about point C to point B. So let's rewrite it. The velocity of C equals the velocity of B plus the angular velocity of this rigid body, so BC, crossed with the position vector from B to C. So that's like written like this. Okay, it's important that we know it's from B to C because if we do from C to B, it's going to give us different value because vectors have a direction and signs to their components. So we know this value, they gave that to us. And we know this from geometry because they gave us dimensions. But we don't know what the velocity of B is. Well, that's fine. We talked about this. We can relate B to A because they're on the same rigid body. So let's write that out. So the velocity of B equals the velocity of A plus the angular velocity of the specific body, so AB, crossed with the position vector from A to B, like this. So now we know this from geometry. They gave us this, and we found that this is stationary, so that's 0. So now we know everything we need to know in order to find the only unknown holding us back from finding the velocity of C, which is VB. So let's solve that. VB equals, well, what's the angular velocity of AB? They gave that to us. It's going to be 2. Let's make sure that it's actually positive and not negative. So let's see. AB is counterclockwise. So when the coordinate system, these axes are set up where y is like this and x is like this, then counterclockwise gives you a positive k vector. And then clockwise would give you a negative k vector. So let's use a positive value crossed with the position vector from A to B. So let's look. Where's A? So it's right here. We need to go to B, so that's going to be a positive 3 I hat plus, and then we need to go from here to here. That's going to be 5.5 minus 1.6, and that's 3.9 J hat. Perfect. Okay, so now we have all of our unknowns in order to find VB. So let's do that. So VB equals, and then also I'm not going to be doing the cross product. I'll be doing a video on the cross product in a different video, but for now I'm not going to, just to save some time. So VB equals negative 7.8 I hat plus 6 J hat. Okay, perfect. So now we found VB and we can plug it into this equation to find what velocity of C is. So the velocity of C equals this, because we're plugging it in. And then we need this term right here. They gave that to us, so plus 4. And is it counterclockwise? Yes, it is. BC is counterclockwise, so it's positive. So K crossed with the position vector right here. So the position from B to C, let's erase that, from B to C, so we go over to the right 2.8, so 2.3 I hat, and then we go down from B to C by 0.5. So B is at 5.5 and C is at 5. So that's 5.5, or that's 0.5. 0.5, and make sure that's a negative, J hat. Okay, now we need to do this cross product, and that would give us negative 2 I hat minus 9.2 J hat, and then we need to bring these over. And then we can equate the I hat components with the other I hat components, and then equate all the J hat components together to get one singular value for both components. So that would give you, you would add these together, and then you would add these together, and that gives you negative 9.8 I hat minus 3.2 J hat. And then don't forget your units. That's a silly way to lose points. And that gives you the velocity vector of a point when you're relating it to other points on a rigid body, or a rigid body that is connected by a common point, such as B in this problem. So let's see, does this answer make sense? So point C is going to be moving in the negative I hat direction, so it's going to be moving this way, and it's also going to be moving down. So does that make sense with the angular velocity that they gave us, which is counterclockwise? Well, yes, because when this moves like this point is going to be moving to the left and down. So our components make sense. Do the magnitudes make sense? I don't know. We'll have to double check our work. It doesn't seem like it's going to be flying around like at a dangerous speed, but we can definitely say that the direction of this vector makes sense. So I hope this helped you guys. I'll see you in the next video.